Okay, folks, looks like the quiz is pretty well timed out. Interesting quiz today. Pretty much had an easy problem and a little bit harder problem on it. With the kinetic energy problem, pretty much almost all of you guys got that one, so that would be absolutely expected, so that's excellent. The Haber process problem was a little more involved, and it shows how we kind of have to go back and deal with concepts that are important that we covered in other chapters. This actually takes you back to the reactions chapter where we did limiting and excess reactants and theoretical yields and all that kind of stuff. So here we're essentially applying gas laws in terms of volumes and number of moles, and we're at STP, so that means we can use our shortcut of 22.4 liters per mole because we're under standard temperature pressure conditions, so it's an easy way to get between moles and volumes. So basically on that one, you have to find a limiting reactant. They give you volumes, you got to convert the volumes to moles. Use your moles to do a mole-to-mole relationship, get a limiting reactant. Once you got that, you can do an excess reactant calculation. And then once you have the excess reactant, you got to take that back to liters again. So a little bit more involved, but it shows how you basically need to go back and look at stuff that's important that kind of crops back up from time to time that we dealt with in prior chapters. And that's something that's true about chemistry. The material builds on itself. So you're constantly going back and using important concepts from previous chapters. So we can't really forget about them. They're always kind of there hovering in the background ready for us. And that's why it's important also to continue to practice. So, you go into those gas law stoichiometry problems in the homework, there are going to be problems that are similar to that you can do that kind of bring those old concepts back to the forefront, which is important. All right, guys, so let's talk a little bit about thermochemistry conventions. So this is building on the video from last night. So just again, to recap a few important things, when we're talking about thermochemistry, there are really two important variables that we have to think about. Okay, so one of them, let's see if I can get this thing to write. For some reason it decides it doesn't want to write today. Oh, there we go. All right, so I've got Q, and Q is called heat. Okay, so heat is one thing that can be transferred during the course of a chemical reaction. A reaction can give off heat or a reaction can take in heat. So that's one thing we have to keep track of. The other is work. All right, so either work can be done by a reaction or work can be done on a reaction. And as we said in the video, this is really dealing with expansion or compression of gases associated with a chemical reaction. All right, both of them are going to be measured in terms of joules. And if we go back and remember what we learned from the video, we found out that a joule is the same thing as a Newton times a meter. This goes back to some of the gas law stuff that we talked about. And if I break it down into its basic SI unit components, I end up getting a kilogram times a meter squared over a second squared. Okay, so those are the units we use for energy. Okay, so heat's a form of energy, work is a form of energy. So now when we think about heat and work and we try to think about it in terms of a system, now remember, what is the system? From the video, we learned that the system is the point of focus. So in most cases, if we're talking about thermochemistry, that's the reaction itself. Okay, so for a given system, if we want to determine the total energy of the system, we can do that in terms of what we call U, which is the internal energy of the system. And the internal energy is defined as the total energy possessed by the system at any given time. Okay, well, how did we define energy? Well, we said there are two types of energy that we can have. We can have heat or we can have work. So if we want to define the total energy or the internal energy has to be the sum at any given time between the heat and the work possessed by the system. So it's Q plus W. Okay, both are measured in joules. So that means internal energy is also going to be measured in joules. All right. So now if we consider this, we have to think about some sign conventions. All right, so here's the situation. If either Q or W is greater than 0, okay, so that means a positive value, that means I have energy entering into the system. And that makes sense, right? Because if it's a positive value, that means the internal energy U is becoming more positive. And that means now that I'm putting more energy into the system. So the system at any given time will possess more energy if that's the case. Now, there's another sort of subset of this when we're talking about Q. If Q, and this is a term thing, is greater than 0, we say that that is an endothermic change or process. Endo meaning going into. Okay, endothermic. So let's look at the other situation. What if we had a Q or a W being less than 0? In other words, taking on a negative value. Well, that would suggest then that energy is exiting or leaving the system. So if energy is leaving the system, what's that doing to the internal energy? Well, that's decreasing it. So that would make sense, okay? And again, a Q convention here. So if our Q or our heat is less than 0, we say that that is an exothermic process. Exo meaning leaving. So I use those terms endothermic and exothermic quite often, so we have to keep track of that. Endothermic means heat is moving into the system. Exothermic means that heat is leaving the system. All right, so these sign conventions become kind of important here. So a positive Q or a positive W means energy in. A negative Q or a negative W means energy out. Again, referencing the system, okay? Now, if we're referencing the system, we could also talk about what the energy is doing with respect to the surroundings, right? So if heat is leaving the system, that's an exothermic process from the system's point of view, but the heat has to be entering the surroundings, okay? So keep track that this is all a fluid process where we have energy moving from one place to another. All right, any questions so far, guys? This making sense? Okay, good. So there's one other thing that we have to think about before we start getting into some of the math here. And that is, for a chemical system, how do we define work? And we already kind of talked about this a little bit. Well, we define work in terms of a gaseous product expanding against its surroundings or being compressed. All right. So we could imagine, for example, an expanding gas. So if we have a gas from a chemical reaction that's expanding against its surroundings, we can say it's doing work against its surroundings, right? Because it's moving molecules out of the way. It's a force times a distance when we think about it from that perspective, and that's work. All right. So how do I define it? Well, my work term now becomes something called pressure volume work. And from the perspective of convention, we put a negative in front of it. So it's a minus P times a delta V. Okay. Now, what do I mean by a delta V? Well, a delta V is a change in volume. So anytime you see that delta in front of something, it means a change in. So that's a volume final minus a volume initial. Okay. So I'm talking about a difference in volume for example, as a gas expands against a constant pressure P. All right. Now, if you look at this, what should the units of this be? Well, pressure is normally in terms of atmospheres, right? And volumes normally in terms of liters. So it turns out that what we would have here in terms of the work term is an atmosphere times a liter. But wait a minute, that doesn't really make sense, because what did I tell you before that the units of work ought to be? Was it atmosphere liters or something else? Well, it can be atmosphere liters, right? But what's the more conventional unit we use for work?
Joule.
Joule, yeah, exactly right. So in order to make this work in terms of problems, we kind of need a conversion between atmosphere liters and joules, and we have that conversion. Turns out that 1 atmosphere liter is equal to 101.3 joules. Okay, so I could express my work term in terms of either one of these units, but more than likely, if we're going to be plugging work back into the internal energy equation, we probably want to be using it in terms of joules so we can compare apples and apples. All right. So now if I plug everything back in, I can come up with my new equation for internal energy. So remember that U is equal to Q plus W, but now I could rewrite it as Q minus P times delta V. Okay, so that's another way of expressing my internal energy. All right, everybody good with that so far? So let's just kind of look at a simple problem, and let's just focus on the work term. This is just a simple example that we can do. So I'll define it here. We want to calculate the work associated with a 3.5 liter expansion of a gas against a pressure of, let's see, 748 millimeters of mercury. And we want to do it 3 ways. We first want to do it in terms of atmosphere liters or liter atmospheres. Then we want to convert it to joules. And then finally, there's another unit of energy that we often see called the calorie. That's a small CAL as opposed to a big CAL. Okay, so we'll just basically look at all of these options here. All right, so first of all, for part A here, I know how to calculate work. Work is equal to minus P times delta V, right? So I can go ahead and do the pressure conversion inside of here. So it's a minus, and I'm going to have what, 748 millimeters of mercury. All right, and I know that 1 atmosphere is what, 760 millimeters of mercury. All that good stuff from the previous gas law chapter we have to remember. And what's my delta V? Okay, it turns out I've got a 3.5 liter expansion. So I'm going to go ahead and multiply by 3.5 liters here. So that's the change in volume that I'm seeing here. And what I'm going to get is a minus 3.4 atmosphere liter change in work or energy. Okay, now keep in mind, it's negative here. Does it make sense that it's negative? Think back to the problem that we've got. A gas is expanding against its environment. Okay, so if a gas is expanding, is it doing work or is work being done onto it? What do you guys think? So if a gas is expanding, it's doing work. That's exactly right. It's expanding out against its environment. So if it's doing work on its surroundings, should the value be negative or positive?
Positive.
Careful. Go back to your sign conventions we talked about, right? If the system is doing work, that's kind of the same thing as saying it's expending energy, right? So work or energy is leaving the system because I'm doing work on the surroundings. Does that make sense? So if energy is leaving the system, it has to be negative. If energy is coming back into the system, it has to be positive. In this case, we are doing work. Think about, for example, picking something up or pushing something against, or pushing an object along a table or something like that. Okay. So in that case, are you doing work on the object? Yeah, you are.
Would this mean that compression would be positive?
The pressure, did you say?
So would that mean that compression would be positive? Because
Yeah, I got you
expansion
now.
is negative. Okay.
Yeah, you're exactly right. Because if I were actually compressing a gas, I'm doing work on the system, aren't I? So I'm putting energy into the system to compress the gas. So that would cause the total internal energy of the system to go up. So you're exactly right. Compression is positive. So expansion is negative, compression is positive. Very good. All right, so the sign makes sense here, guys. And again, this is not terribly hard, but you kind of have to get your brain wrapped around it. And once you do, it kind of makes sense. So we want to go to joules next. So I'm going to take my atmosphere liters. So I got minus 3.4 atmosphere liters. All right. And now I got a conversion factor that gets me to joules, don't I? So I know that for every 1 atmosphere liter, I'm going to have 101.3 joules. Okay, so that gets me to a more useful place because now I can compare joules to joules if I want to plug this back into an internal energy equation. And as sig figs, I get minus 3.5 times 10 to the second joules. Okay, still negative because, again, the system is still doing work on its surroundings. So the internal energy of the system should be decreasing. And then finally, just introduce this last little conversion. 1 calorie, that's a little c for calorie, because the big C is your dietary calorie. So that's a different thing. So we use little c's normally when we talk about thermodynamics. That's 4.184 joules. And that's a number you'll see actually in the next video too that has some other significance associated with it. So I'll go ahead and take my joule value here. So minus 3.5 times 10 to the second joules. All right, and I want to go to calories, right? So I know that 1 calorie is 4.184 joules. Okay, joules will cancel and I'll end up with minus 83 calories. Okay, so those are all the normal units of energy that we could usually run into. So normally we'll have atmosphere liters. If we're talking about a work term, we can convert to joules, and joules and calories can be converted between as well. So we've kind of introduced all those different energy conversions that we might need at this point. All right, everybody good? All right, let's look at another one, because again, I think example problems kind of help us to think about how to think about these sign conventions especially. All right, so let's say if 325 joules of work is done by a system at a pressure of 1.0 atmospheres and 298 Kelvin. What is the change in volume of the system? All right. And the other thing we could ask along here, and we could probably figure out right away, is did the volume expand or contract? we could probably predict that. So think about that for just a second. In other words, is this an expansion or a compression? Okay, now the trick here is going back to asking, is work being done by the system or on the system? So what did we actually say here? The work is being done by the system, okay? So if we're thinking about this in terms of a delta V associated with a gas, work is being done by the system, right? Is energy leaving the system or entering the system? What do you guys think?
Leaving?
It's leaving the system. Yeah, that's exactly right. So if the work term is getting smaller, right, that suggests that work is being done by the system on the surroundings. Okay, so would this be an expansion or a contraction?
Expansion?
Yeah, exactly. It's just like our last problem that we did. Because yeah, if the work is being done by the system on the surroundings, that has to be an expansion of a gas against its surroundings. Okay, so we would predict here that this is an expansion. And we can show that, all right? So let's go back and see what we know. Okay, we know that the work is equal to 325 joules. Okay, now I got to put a sign on this, don't I? And again, that 325 joules could either be positive or negative, again, depending upon our perspective. So our perspective here, of course, is the system. And we said that the work is being done by the system. Okay, so what do I put in front of that joules? Is it negative or positive? Is this positive work or negative work from the standpoint of the system? What do you guys think?
Negative.
Negative.
Yeah, you got it. It's negative. Why? Because the system is doing work on its surroundings. So that means the total internal energy of the system is decreasing because the work is decreasing. Very good. Very good. All right. And I also know that work is equal to minus P times delta V. That's again another definition that we have. So I want delta V. So let's solve for delta V. So delta V is going to equal to minus the work divided by the pressure. Okay, so let's stick some numbers in here. I got to carry that negative through. So now I've got a minus 325 I'm going to stick in for the work. Okay. And I got a pressure, right? The pressure is 1.0 atmospheres because that's what I'm expanding against. All right. So notice what happens to the negative signs there. They cancel each other out, right? So my delta V turns out to be 325 positive joules per atmosphere. Okay. That seems like a really weird unit for a volume, doesn't it? Oh, but we have a fix for that, right? Because remember, I have this conversion that I can apply. I know that 1 liter atmosphere, to get rid of the joules, right, is 101.3 joules. Okay, so joules cancel with joules, atmospheres cancel with atmospheres, and look what I get. I get liters back out of this. All right, so now I end up getting 3.2 liters. Now notice it's a positive value, right? It's a positive value. So would I expect the delta V or the change in volume to be positive in this case? Yeah, because we said that we probably had an expansion here because the system is doing work on the surroundings. So I would expect a positive delta V for that. What if I had a negative delta V? That would suggest a compression, wouldn't it? In other words, the final volume would be smaller than the initial volume. But this is an expansion, so I'd expect my change in volume to be positive, again, from the reference point of my system. All right, does that make sense to everybody? So again, we're basically just trying to get comfortable with these sign conventions more than anything else, as well as definitions. Let's do one more. All right, so let's do this. What is the change in internal energy. So we'll just say in U of a system. If the system, so we'll bring heat back into this, evolves 289 calories of heat, and has 1.25 kilojoules of work done on it. All right, so this is nice because we again have to think about the total change in internal energy as there's a change in heat and a change in work applied to the system. All right, so basically let's look at our Q and our W, but let's remember first that I can define internal energy as the sum of Q plus W. Okay, so now I independently need my Q value and my W value. Now remember, Q's heat, isn't it? Okay, so what do I know about heat? All right, it says the system evolves 289 calories of heat. Now, the term evolves, what does that suggest to you? Heat leaving the system or heat entering the system?
Entering.
So evolves means giving off, right? Evolves actually means leaving, giving off. All right, so that suggests that I need a negative in front of my Q. Okay, so my Q here is going to equal to minus 289 calories. For example, let me just give you another example where we might use that term evolve. So you might say in a certain chemical reaction, a gaseous product is evolved. So that means gas is given off by the chemical process. Okay, so that's sort of what that means, in case you haven't run into that term before. So let's go ahead and get it in terms of joules because, well, that makes sense because our work is in terms of kilojoules. So we might as well get everything to joules. All right, so I know that in 1 calorie, I got 4.184 joules. Okay, so calories cancel with calories, and I get minus 1209 joules. Okay, and that's going to be good to 3 sig figs, it looks like there. Let's do the work. Now, what does it say about the work? It has 125 kilojoules of work done on it. Okay, so what should the sign of work be if the work is being done on the system? Positive or negative?
Positive?
Yeah, you got it. Yes, perfect. So that's going to be 1.25 positive kilojoules. Let's take it to joules so we can compare the two things. So let's see, in 1 kilojoule of work, I've got 1,000 joules of it. And I've got 1,250 joules of work. Again, good to 3 sig figs here. All right, so again, going back to my internal energy here, my U is my Q plus my W. So what's my Q? It's minus 1209 joules, right? And I got to add to that the work term, which is 1250. Also good to 3 sig figs. And then when I work that out, I've got a positive term and I got a negative term. And it turns out the positive term actually wins out here. So you end up with about 41 joules. Okay. And let's see, that turns out to be good to that 3rd place there. So Lewington turns out we're really only good to 40 because we're only good to significance on that 4 there. So about 40 joules positive is my internal energy. Okay, so it turns out in this case, yeah, the positive wins over the negative. So I still have a positive internal energy after these 2 changes have occurred to my system. So again, it's remembering what those definitions are and remembering sign conventions. In other words, does Q have to be positive or negative? Does W need to be positive or negative? Again, that depends upon whether energy is going into the system or energy is leaving the system in each case. All right, everybody good with that? All right, so I have about 10 minutes worth of Chem 101 for us to do. It's actually a really easy little assignment. I was just looking at it a little bit ago. So let me pop that over and grab it. So it's my first thermochemistry assignment. And it looks like it's just heat and work, about 10 minutes. You probably won't even need that long to do it. And we'll go ahead and start it. Have a look at it here. Yeah, really easy stuff for the most part. I was looking at number 3 there, guys. Watch your units on that one, right? You're calculating kinetic energy. It's 1/2 mass times velocity squared. Watch your mass units on that one. So remember what the units of energy have to be: kilogram meters squared per second squared.